we're doing something a little bit different. We're going to try and take a research paper and just break it down piece by piece,
Yep.
kind of like a guide for how to read these papers.
Yeah.
And I think this will be really useful for, anyone who's new to the research game.
Yeah.
Maybe you're feeling a bit intimidated by those really dense academic papers out there.
For sure.
But I think once we unpack it together,
Yeah.
piece by piece,
Yeah.
we'll see. It's not as scary as it seems.
Definitely.
So I'm Henry, and I'm joined by Julie, an expert in visual object recognition and deep neural networks.
Hi, everyone.
So Julie, the paper we're tackling today is called Comparing Deep Neural Networks Against Humans. Object recognition when the signal gets weaker? What got you interested in this paper?
Well, I think what's so fascinating about this paper is that it tackles this really fundamental question of how do deep neural networks measure up against us, the human visual system? And, we're talking about DNNs designed for visual tasks, and they go beyond just looking at overall accuracy. They delve into how humans and DNNs process information differently, particularly when things get a little tricky. When an image is blurry or low contrast or noisy.
Gotcha. So it's not just about who wins, but how they play the game.
Exactly.
Yeah.
It's about understanding the strengths and weaknesses of both human and artificial vision.
Awesome. So before we jump into all the nitty-gritty, can you give us just like a quick overview of what this research is all about?
Sure. So the researchers basically wanted to see how well DNNs can recognize objects when the visual information is not perfect.
Right.
So they compared the performance of 3 well-known DNN architectures. These are AlexNet, GoogLeNet, and VGG16 against human participants.
Okay.
And they did this by putting them through a series of challenges,
Right.
like removing color information, reducing contrast, adding visual noise, and even using a new method called eidolon distortions to mimic the blurriness of our peripheral vision.
Eidolon distortions. That sounds pretty intense.
It is, and it's a really clever way to test how well both humans and DNNs can generalize to new types of visual challenges.
Okay, so we've got our contenders, we've got our challenges.
Yeah.
Let's dive into the first round, color versus grayscale.
All right, so in this test, they took images that were originally in color and converted them to grayscale and then showed these images to both the DNNs and the human participants and measured how well they could still recognize the objects.
So did taking away the color information throw off the DNNs?
It did, actually. All 3 DNNs showed a significant drop in performance when presented with grayscale images. This suggests that they rely heavily on color as a key feature for object recognition.
Okay.
Which, makes sense considering they're typically trained on massive data sets of color images.
Oh, so they're like those kids who only eat like beige food.
Yeah.
They're not used to anything outside their comfort zone.
That's a great analogy.
Yeah. But humans, on the other hand, barely even noticed the lack of color. Our visual system is incredibly robust. We can recognize objects in a wide range of lighting conditions and color palettes,
Yeah.
even black and white photographs. It's amazing.
Yeah.
It's like we have this backup generator for visual recognition.
Exactly.
But why is human vision so resilient to these changes? What's going on in our brains?
Well, one key factor is that our brains don't just rely on one visual cue like color.
Right.
We use a combination of cues, shape, texture, context, even our prior knowledge about the world to build this rich, multidimensional representation of what we're seeing.
So it's like having this whole team of visual detectives working together, each one specializing in a different aspect of the scene.
Right.
And if one detective's out sick, the others can fill in the gaps.
Exactly.
Yeah, and this multimodal processing,
Yeah.
that's what allows us to be so adaptable.
Exactly.
Okay, so humans win round 1. But let's see how they fare in the next challenge.
Yeah.
Contrast reduction. What do the researchers do here?
Yeah. So in this test, they gradually decrease the contrast of the images, making them progressively harder to see.
Okay.
Imagine turning down the brightness on your screen until the details start to fade away.
Okay, I can picture that.
Yeah.
So how did our contenders handle this dimming of the lights?
So as the contrast was reduced, the performance of all 3 DNNs started to decline, particularly AlexNet and GoogleNet. Their accuracy dropped significantly, indicating that they struggled to extract meaningful information from the images when the contrast was low.
So they're like drivers who get blinded by oncoming headlights.
Yeah.
They can't see well in low light conditions.
Exactly.
Yeah.
And it highlights the fact that these DNNs are typically trained on high-quality images with good contrast. So when the visual signal gets weaker, they're not as reliable.
You mentioned that VGG16 was a bit more resilient.
Yes, VGG16 did show a bit more resilience to contrast reduction than the other two DNNs. This suggests that there might be some subtle differences in how these networks are structured and trained that affect their robustness.
Interesting. So even within the world of DNNs, there's variation in how they handle these challenges.
Absolutely. It's not a one-size-fits-all situation. Each architecture has its own strengths and weaknesses.
Gotcha. But what about the human participants? Did they maintain their dominance?
They did. Humans continued to outperform the DNNs even as the contrast decreased significantly.
Okay.
Our visual system has evolved to handle a wide range of contrast levels, from the bright glare of sunlight to the dim light of twilight. We can see clearly in conditions that would completely stump these DNNs.
2 for 2.
Huh.
Humans are really showing off their visual superpowers here. But I have a feeling things are about to get even tougher. What's next on this obstacle course?
Next up is the noise invasion test.
Okay.
This is where things get really interesting.
Right.
The researchers added visual noise to the images,
Okay.
similar to the static you used to see on old TV screens. This makes it much more challenging to distinguish the objects,
Got it.
because the noise interferes with the visual signal.
So it's like trying to recognize your friend in a crowded, noisy room.
Exactly.
Yeah, there's a lot of distractions and interference.
Yeah. And this test really exposed the limitations of current DNNs. Even a small amount of noise caused their accuracy to plummet.
Mm.
They were essentially thrown off completely by this disruption.
So they're kind of like those people who can't focus when there's any background noise.
Yeah,
They need perfect silence to function properly.
that's a good way to put it.
Yeah. But humans, on the other hand, barely flinched. We're incredibly good at filtering out noise and focusing on the important visual information.
That's right.
It's like we have built-in noise-canceling headphones for our vision.
Yeah.
But how do our brains do that? What's the secret sauce?
It's a combination of factors, really.
Yeah.
Part of it is our brain's ability to predict what we're likely to see based on our past experiences and the context of the situation.
So it's like our brains are constantly making educated guesses about what's out there,
Uh-huh.
and they're surprisingly good at it.
Exactly. And this predictive processing helps us fill in the gaps when the visual information is incomplete or noisy.
Right.
But there's more to it than that. Our brains also have sophisticated mechanisms for suppressing irrelevant information and amplifying the signals that are most important for the task at hand.
So we're not just passively absorbing everything we see.
Right.
We're actively shaping and filtering the visual information to make sense of the world.
That's right. It's a dynamic and interactive process, and it's what allows us to see clearly even in the most challenging conditions.
Okay. So humans have aced 3 tests in a row. But the researchers didn't stop there, did they? They had one more trick up their sleeve, right? Something called eidolon distortions.
Yes, that's right. The Eidolon test was a particularly clever addition to the study because it introduced a new type of visual challenge that hadn't been extensively studied before. Instead of simply degrading the images by removing color contrast or adding noise, they used these Eidolon distortions to mimic the blurriness of our peripheral vision.
I'm curious, why focus on peripheral vision? It's not exactly known for its clarity.
That's true, but it's a crucial part of how we see the world. While our central vision is responsible for sharp, detailed vision,
Okay.
our peripheral vision provides us with a wider field of view and helps us detect movement and changes in our surroundings.
So it's like having a built-in security camera
Yeah.
that's constantly scanning the environment for potential threats or opportunities.
Exactly.
Yeah, and what's fascinating is that even though our peripheral vision is less accurate than our central vision,
Right.
humans still outperform the DNNs across various levels of eidolon distortion.
Yeah.
So even when we're not looking directly at something, we're still able to glean meaningful information from our peripheral vision.
Right.
And we're better at it than these sophisticated DNNs.
Yeah. It speaks to the adaptability and sophistication of human vision. We can generalize well to new types of distortions, suggesting that our brains have learned a more flexible and robust representation of objects than what the DNNs have been able to achieve so far.
Okay, so humans are 4 for 4. It's clear that we have a remarkable ability to handle visual challenges that completely stump these DNNs. But the researchers didn't just stop at overall accuracy, did they? They dug deeper into the types of errors that humans and DNNs were making.
You're exactly right. They wanted to understand not just who was getting the answers right, but how they were arriving at those answers. And for that, they used a technique called confusion matrices.
Now, I know confusion matrices can be a little tricky to grasp, especially if you're new to research.
Yeah.
Can you break it down for us? What exactly is a confusion matrix, and what does it tell us about how humans and DNNs make decisions?
So a confusion matrix is essentially a visual tool that helps us analyze the types of errors a model is making. Imagine a table or a matrix where each row represents a category of objects, and each column shows how often the model misclassified an object from that category into a different category.
Gotcha. So it's like a scorecard for mistakes.
Yeah.
We can see which categories are tripping up the model the most.
Exactly. And what the researchers found is that as the tasks got harder, the DNNs became increasingly biased towards just a few specific categories.
Okay.
It's like they were simplifying the problem in a way that humans don't.
Hmm.
For example, if they saw something round and fuzzy, they might always classify it as a teddy bear, even if it was actually a dog or a fluffy pillow.
Right.
They were relying on a limited set of features and making sweeping generalizations.
So they're kind of like those people who judge a book by its cover,
Yeah,
making snap judgments based on superficial cues rather than taking in the whole picture.
that's a great way to put it.
Yeah. Humans, on the other hand, are much more nuanced in our decision-making.
Mm.
We consider multiple factors, weigh the evidence, and are more willing to revise our initial judgments as new information comes in. Okay, so confusion matrices give us this fascinating peek into the thought process, so to speak,
Yeah,
of both humans and DNNs.
yeah.
They reveal not just how accurate they are, but how they approach the problem of object recognition.
Exactly. And what we see is that while DNNs have made impressive strides, they still approach visual tasks in a fundamentally different way than humans. They're more rigid, less adaptable, and more prone to oversimplification.
This has been an incredibly insightful look into the world of visual object recognition.
Huh?
We've seen how humans consistently outperform DNNs when the visual signal gets weaker, and we've even gotten a glimpse into why that might be.
Mm.
But I'm sure our listeners are wondering, what does this all mean in the bigger picture? Why should we care about these differences between human and artificial vision?
That's a great question, and it's one we'll delve into more deeply in the next part of our deep dive.
Okay.
We'll explore the implications of these findings for real-world applications, from autonomous driving to medical image analysis, and we'll discuss what we can learn from the remarkable resilience of human vision. Stay tuned.
Welcome back. We've been exploring this fascinating research that really puts human and machine vision to the test. We've seen humans win every round so far. But as we dive deeper, the question becomes, what's the research? So what? Of all this, Julie, what do these findings mean for the real world, for fields beyond just research labs?
Yeah, that's where it gets really exciting, because
No.
understanding the limitations of DNNs, especially compared to human vision, is crucial if we want to develop AI systems that we can truly rely on. Think about all the areas where AI is already making a big impact: self-driving cars, medical diagnoses, even robots working in factories.
Okay, let's take those one by one.
Yeah.
Self-driving cars, that's the dream for a lot of folks. No more traffic jams. Everyone can relax and read a book or maybe catch up on a podcast episode like this one. But how does this research connect to that world?
While a self-driving car relies heavily on computer vision to navigate, it needs to identify pedestrians, other vehicles, signs, obstacles, everything we humans just take for granted when we're behind the wheel. But as we've seen, current DNNs can get easily tripped up when the visual information is not perfect. Imagine a rainy day, the glare on the road, maybe some fog rolling in.
Suddenly, that relaxing commute sounds a lot more stressful if the AI driving the car isn't as adaptable as a human driver.
Exactly. The real world is messy. We've got weather conditions, unexpected objects, even just the way the light falls at different times of day.
Right.
This research is a reminder that while DNNs are powerful, they're not invincible. We need to make them more robust if we want self-driving cars to be truly safe and reliable.
That makes sense. So what about medical image analysis? I know AI is playing a bigger role there too.
Absolutely. Doctors are using AI to help analyze things like X-rays, CT scans, MRIs, all sorts of medical images. And it's incredibly helpful, especially when it comes to spotting subtle patterns that a human eye might miss. But here again, those images aren't always perfect.
Right? There might be noise,
Mhm.
low contrast, all the challenges we talked about earlier.
Exactly.
And in the medical field, a mistake could have serious consequences.
Exactly. This is where understanding the resilience of human vision is so important. Doctors use their knowledge, their experience, their visual skills to interpret those images even when they're not crystal clear. We need to find ways to build that same kind of adaptability into AI systems.
It's almost like teaching the AI to think like a doctor, not just recognize patterns.
That's a great way to put it. It's not just about matching pixels. It's about understanding the context, the nuances, all the things that make human vision so powerful.
So we've talked about cars. We've talked about medicine. What about robotics?
Yeah.
I feel like robots are becoming more and more common in our lives.
They are, and they rely on computer vision for so many tasks, from sorting packages in a warehouse to performing delicate surgery. But again, those robots need to be able to operate in the real world with all its unpredictability. Imagine a robot working in a dimly lit factory or trying to rescue someone from a smoky building.
Those are some pretty tough conditions even for a human.
Exactly. This research highlights just how far we need to go in making DNNs more robust. We need robots that can adapt to changing light, unexpected obstacles, all the things that humans can handle instinctively.
So are you saying that the future of AI depends on learning from human vision?
In a way, yes. We've spent decades trying to build AI that can match or even surpass human intelligence, and in some areas we've made amazing progress. But when it comes to vision, especially in the real world, humans are still the champions.
So we need to figure out what makes us so good at it and translate that into the algorithms that power AI.
Exactly. It's not about giving up on DNNs. They're incredibly powerful tools.
Yeah.
But we need to find ways to make them more adaptable, more resilient, more like us.
Okay, so how do we do that? Is there a way to bridge the gap between human and machine vision?
Researchers are exploring a lot of different approaches. One promising avenue is to develop DNNs that can integrate information from multiple sources, just like our brains do.
So instead of just looking at an image, the AI might also take into account sound texture, even context. It's like giving it a more holistic view of the world.
Exactly. Another exciting area is something called neuromorphic computing. This involves designing computer chips that mimic the structure and function of the human brain.
So instead of trying to force our traditional computers to think like humans, we're building new hardware that's inherently more brain-like.
Right. It's a radical approach, but it has the potential to revolutionize AI and lead to systems that are far more adaptable and efficient than anything we have today.
So it's a combination of new algorithms and new hardware.
Exactly. It's a multifaceted challenge, and it's going to require a lot of innovation and collaboration across different fields.
It's pretty inspiring, actually. We're
Wow.
using the incredible power of human vision as a roadmap for building the next generation of AI.
And what's even more exciting is that the more we study human vision, the more we realize how much we still don't know.
So it's a journey of discovery on both fronts, understanding our own brains and building AI that can rival them.
Absolutely. And who knows what amazing breakthroughs lie ahead.
Okay, Julie, this has been a fantastic deep dive into the world of visual object recognition. We've learned about the strengths and weaknesses of DNNs, the remarkable resilience of human vision, and the exciting possibilities for the future of AI. But before we wrap up, I want to come back to our original goal for this episode. We wanted to make this research accessible to new researchers, those who might be feeling a little intimidated by the world of scientific literature.
Right. We wanted to break down this complex topic into something understandable and engaging.
So if someone was listening to this and feeling inspired to go read the actual research paper, what advice would you give them?
Don't be afraid to jump in. I know research papers can seem daunting, but they're really not as scary as they look. Just take it one step at a time.
And remember, you don't have to understand every single detail on the first read-through.
Exactly. Focus on the big picture. What question were the researchers trying to answer? What methods did they use? What were their main findings? And don't hesitate to look up terms you're not familiar with or to reread sections that seem confusing.
It's a process just like any form of learning.
Yeah,
And the more you practice, the easier it gets.
absolutely. And remember, even experienced researchers have to read papers multiple times to fully grasp all the nuances.
So don't be discouraged if it takes time and effort. The rewards are definitely worth it. You're opening yourself up to a world of knowledge and discovery.
Exactly. And you never know. You might even find yourself inspired to embark on your own research journey.
Welcome back to the deep dive. So far, we've uncovered some really interesting insights about human and machine vision. We've seen that humans are incredibly good at navigating the messiness of real-world visual data, even when those sophisticated DNNs struggle. I'm curious, Julie, as we kind of wrap up our deep dive into this research, what are your biggest takeaways? What's got you thinking?
What really stands out to me is just how adaptable and resilient human vision is. We can effortlessly handle all those visual challenges that still trip up even the most advanced DNNs. And the more we understand about how our brains do that, the better equipped we'll be to build more robust and reliable AI systems.
Yeah, we've touched on some of the reasons behind this human superpower, right? Like Our ability to integrate information from multiple sources, not just relying on color or shape alone.
Exactly. It's like we're constantly piecing together a puzzle using every clue we can get our hands on, shape, texture, context, even our prior knowledge about the world.
Hmm.
If one piece is missing or distorted, we can still figure out the overall picture.
And our brains are so good at filtering out distractions too, focusing on what's important. We saw that in the noise invasion test, where humans barely even noticed the static that completely threw off the DNNs.
That's right. Our brains are like master editors, constantly sifting through the visual information and highlighting the most relevant parts. And this ability to selectively attend to what matters is crucial for navigating a world that's full of visual clutter.
So it's not just about recognizing objects in isolation. It's about understanding the whole scene, the relationships between objects, even predicting what might happen next.
Exactly. Our brains are constantly making predictions about the world based on our past experiences and the current context. And these predictions help us fill in the gaps when the visual information is incomplete or ambiguous. It's like having a sixth sense for what's likely to happen.
And this predictive power is something that current DNNs are still struggling to master, right?
Absolutely. They're getting better at recognizing patterns, but they're not as good at understanding the underlying dynamics of the world, the way things move and interact. And that's a crucial step if we want to build AI systems that can truly reason and make decisions like humans do.
This has been such a fascinating journey, Julie. We've delved into this intricate world of visual object recognition, explored the strengths and weaknesses of both human and artificial intelligence, and uncovered some really thought-provoking insights. As we wrap up our deep dive, what's the key message you hope our listeners take away from this episode?
I think the biggest takeaway is that we can learn a lot from studying human vision. It's an incredibly powerful and adaptable system honed over millions of years of evolution. And by understanding how our brains process visual information, we can gain valuable insights that will guide the development of more robust, reliable, and intelligent AI systems.
It's almost like human vision is a blueprint for the future of AI.
In a way, yes.
Mm.
It gives us a glimpse of what's possible, a target to aim for, and who knows what incredible breakthroughs lie ahead as we continue to unravel the mysteries of the human brain and translate those discoveries into the world of artificial intelligence.
Well said, Julie. It's been an absolute pleasure having you on the deep dive. And to our listeners, we hope this episode has sparked your curiosity about the world of research and inspired you to keep exploring this fascinating intersection of human and machine intelligence. Until next time, keep diving deep.